This video will discuss automation of radiological characterization surveys during decommissioning. The characterization of system structures, components, and land areas during decommissioning is typically performed with manual meters. The final status survey is used to show that the site meets the site release limits, intentionally use prescribed survey protocols which are very labor intensive. Automation of these surveys offers substantial benefits. Features of the EPRI demonstrations are equipment that performs automation of detector movements during the surveys, real-time data collection, use of GPS for outdoor surveys, and optical control programs for indoor surveys to create maps for use in programming pathways and displaying results. Use of gamma spectral analysis hardware for immediate radionuclide-specific results, and systems having lowered limits of detection values, no more than 50% of typical site release limits for nuclear power plants. The first phase of the EPRI demonstrations was conducted at the Kewaunee Nuclear Power Station in 2019. In this demonstration, an EPRI prototype system was determined to be suitable for characterization surveys. For open land areas, the system met sensitivity requirements for final status survey for the radionuclide cesium-137. For building floor areas, autonomous floor surveys were performed at a rate of 16 meters squared per minute. These demonstrations showed that additional work was needed to autonomously survey building walls and to demonstrate the system with background levels that are more consistent with those after decontamination. The second phase of the EPRI demonstrations was conducted in 2022. A survey of industry technologies determined that LiDAR-based systems are available that perform autonomous mapping and guidance of robotic systems. Software is also available that can automatically integrate detector readings onto 3D maps created by the system. The goal of the second phase of the EPRI demonstrations was to show the capabilities of these latest technologies to perform autonomous surveys of walls, also to achieve required sensitivity for final status surveys. EPRI chose two suppliers to perform these demonstrations. One was the Createch Limited of the United Kingdom, and the second was Gamma Reality Incorporated of Richmond, California.
The robotic survey system features two detector configurations: upper wall 1 to 3 meters and floor/lower wall. Two sodium iodide detectors able to locate sources that are a small fraction of site release limits.
So the project is to demonstrate an autonomous robotically deployed clearance measurement system. The main reason for this is that it's a manual labour-intensive job currently. So the idea is to do this remotely, do this autonomously and do it very quickly in comparison.
Clearance measurements at nuclear sites are a really great example of a measurement that can be very time-consuming, really onerous, but is also very important to get right because it's the measurement that demonstrates that your site is no longer a nuclear site.
So the technology we're deploying here is a robotic deployed radiation detector system. So there's two radiation detectors and a LiDAR scanner. The idea is that we can monitor the activity in an area, assign it to the specific location in a digital environment, and we can also calculate the minimum detectable activity and the uncertainty. So the user can be confident in real time that you've scanned down to the clearance level that you require. It takes so much time and money for an individual to go through and scan a whole area with a handheld device, whereas this gives you an autonomous option. There's no reason why this couldn't save you a lot of effort and a lot of time and cut down something that might take months to might take weeks.
So the two sensors we've got on this robot are two large sodium iodide crystals, and that gives us quite a key benefit because it allows us to reach quite a low minimum detectable activity, which is exactly what you'd want in this sort of application.
These are really efficient detectors. They can pick up the spectroscopic difference between the measured radioisotope and the natural background from uranium decay train, for example. Additionally to that, it also does automatic waypoints, so it's an autonomous system. It can move around the room without a handheld controller or without anybody being present. You just set the waypoints and off it goes. And furthermore, it does automatic collision detection, so if somebody walks in front of it, it'll stop. If there's an item in the way of the path that you predefined, it will stop and move around it.
So the LiDAR system we're using on the robot is a SLAM system for simultaneous location and mapping that allows the robot to navigate in space and know where it's going, so we can tell it which bits of the building we want to have a look at with the sodium iodide detectors.
Many of the measurements that you have to make during the clearance process will be at height. Working at height can be a significant hazard, and also the things you have to do to protect that hazard can be a significant cost. By eliminating the person at risk, you can eliminate those costs and the hazards. Another great benefit is that robots are extremely good at making very precise and accurate records of everything that they do. So there's an opportunity for a step change in the quality, the level of detail, and the accuracy of the record-keeping process, which is obviously an essential part of clearance measurements.
After navigation, the system created a 3D image of the room. The vehicle moved along the wall to a waypoint, autonomously. System lower limits of detection were well below the typically required of 50% of site release limits. For the demonstration at Gamma Reality, the Gamma Reality system uses autonomous scissor lift to raise and lower the detector to various heights from 1 to 3 meters. One sodium iodide detector used. Sources that are a small fraction of site release limits, including one in a corner, were detected. In addition to showing the location of sources on the 3D image, the source location was also shown on a photo of the scanned area. Sources are shown on the photo with the center of the identified location approximately 30 centimeters from actual source location.
Hello, I'm Andy Hafner, CEO of Gamma Reality Inc. For this demonstration, we integrated our commercial LAMP product with a robot to autonomously scan walls for decommissioning applications. LAMP creates 3D maps by fusing LiDAR and radiation data to localized sources all in real time. We integrated LAMP with a scissor lift and a robot to enable autonomous scanning and mapping of radioactive contamination on walls. Using this approach, we detected and localized the sources at much lower than the legal limits to be shown in 3D and augmented reality. Not only is this approach faster than current methods, but it also gives the end user a clear picture of the location of the sources within the 3D map and camera overlay. Deploying new technologies like LAMP with robotic platforms will enable faster and more efficient mapping, identification, and localization of radioactive sources for nuclear applications, including decommissioning.
After the navigation system created a 3D image of the room, the vehicle moved autonomously while surveying the wall. The system shows source locations on a photo of the scanned area in addition to showing locations on the 3D image.
The summary of these EPRI demonstrations is that systems are available that can perform autonomous surveys of buildings and outdoor land areas. Individual radionuclide concentrations were determined rather than simple gross gamma activity levels of more conventional equipment. Open land area surveys were performed by the EPRI prototype system and achieved detection sensitivities required for final status survey for the radionuclide Cesium-137. Building surveys were performed by both Createch and Gamma Reality systems that detected sources that were a fraction of typical site release limits, while achieving the required detection sensitivity for final status surveys, scanning at rates up to 36 times higher than conventional manual scanning handheld survey meters, and 8 times faster than in situ gamma spectroscopy systems. These systems also located elevated areas in the scan area and displayed those areas on 3D maps created by the system. The final screen will show you where to access more information on EPRI.com and additional YouTube video.